You press play on a Netflix movie, it buffers for 4 seconds, you close the app. Netflix has the data. A buffer event longer than 3 seconds kills 39% of viewers permanently. Now multiply that across 70 million concurrent viewers in 190 countries. Connections range from 1 beat per sec rural DSL to 1 Gbps fiber. A raw 4K HDR movie is 100 gigabytes uncompressed. Streaming that from one central server is physically impossible. So how does Netflix deliver 800 GB per X of outbound traffic at peak with sub 3 second startup every single night? Let's put the numbers in perspective. Netflix serves 260 million subscribers across 190 countries. At peak hours, typically 8 to 11 p.m. local time, they push over 800 Gbps of outbound traffic. That is roughly 15% of all global internet traffic during those windows. Their 2012 Christmas Eve outage, a misconfigured AWS East deployment, lasted 3 hours and traumatized millions of users. That single incident rewrote Netflix's entire architecture philosophy. The lesson became permanent. Never trust one region, never trust one path, and always assume failure is happening right now. This is the founding principle behind everything you're about to see. Think of ABR like a smart highway that changes speed limits based on traffic. Netflix does not encode one video file per title. They encode roughly 20 different versions, called representations, at different resolutions and bit rates. The client player checks available bandwidth every 2 to 4 seconds. It then fetches the next 4-second chunk at the best quality it can sustain. The player maintains a 30-second buffer ahead at all times. If bandwidth drops, the player switches down quality instantly. The viewer sees a soft quality dip, not a freeze. That trade-off saves the experience entirely. But here's the catch. Encoding 20 versions of every title is expensive. Netflix found a smarter way. Traditional platforms use the same bitrate ladder for every title. A cartoon and an action movie get identical quality levels. Netflix discovered this wastes massive bandwidth. BoJack Horseman, a simple animated show, looks perfect at 1000 kbps. Extraction 2, dense visual chaos, needs 4000 kbps for identical perceived quality. In 2015, Netflix deployed the Dynamic Optimizer. It analyzes each title's visual complexity before encoding begins. It then builds a custom bitrate ladder per title. Result, 20% bandwidth reduction with equal or better quality. At Netflix's scale, that is hundreds of gigabits per second saved globally, every hour. In 2018, they pushed further with per-shot encoding, adjusting bitrate at the scene level. Now here's where it gets interesting. Where do those encoded files actually live? Netflix does not primarily use AWS CloudFront or Akamai. They built Open Connect, their own CDN. Open Connect appliances are custom physical servers embedded directly inside ISP networks. AT&T, Comcast, Deutsche Telekom, 1,000+ ISPs globally host these boxes for free. In exchange, ISPs save enormous transit costs by serving Netflix traffic locally. Each appliance holds up to 280 TB of tiered SSD and HDD storage. Network interfaces run at 100 Gbps. When a Netflix user in Chicago presses play, the video comes from inside Comcast's network. RTT drops from 50 to 80 milliseconds down to 1 to 3 milliseconds. As of 2023, Netflix has deployed over 17,000 OCA servers across 6,000+ locations worldwide. The moment you hit play, a precise chain of events fires. The Netflix client sends a play request to the AWS control plane. The playback manifest service authenticates your account, checks your subscription tier, and selects the nearest available OCA server. It returns a manifest file, a small XML or text document listing every quality level and the URL for each 4-second segment. The client downloads this manifest in under 100 milliseconds. It then begins fetching segments directly from the OCA, bypassing AWS entirely for video bytes. The ABR algorithm selects the first quality tier based on initial bandwidth probe. Playback begins. This entire flow, from button press to first frame, takes under 3 seconds on a healthy connection. Here's how ABR decision logic works in practice. The player measures download speed for each segment fetch. It multiplies measured bandwidth by a safety factor of 85%. This prevents rebuffering on sudden drops. It then walks up the bitrate ladder to find the highest quality level the connection can sustain. If the buffer drops below 10 seconds, the player forces a downgrade immediately. No waiting. This is the core loop running inside every Netflix, YouTube, and Disney Plus client player on Earth. The safety factor is the critical tuning knob. Set it too high, you waste bandwidth. Set it too low, you trigger unnecessary quality drops. Netflix landed on 85% after years of real-world telemetry. Netflix does not wait for users to request content before caching it at the edge. Popular titles are proactively pushed to OCAs during off-peak hours, typically 2 to 6 a.m. local time. Long-tail titles, think obscure documentaries, start on AWS S3 origin and get pulled to the OCA on first request, then cached locally. Netflix uses a consistent hashing ring to decide which OCA stores which content. If an OCA is full, least recently used content gets evicted first. This is why hit shows like Squid Game, which exploded to 111 million viewers in 28 days, can be served locally from ISPs without hammering origin servers. This is where it gets interesting. That content must be encrypted. Every Netflix video segment is encrypted before it touches the CDN. DRM keys are never stored inside the OCA files. The client must fetch a decryption key from Netflix's license server separately. This is why piracy is hard. Netflix uses 3 parallel DRM systems simultaneously. Widevine covers Android and Chrome, Google's system. PlayReady covers Windows and Xbox, Microsoft's system. FairPlay covers all Apple devices, Safari, iPhone, Apple TV. The OCA serves only encrypted bytes. The license server running on AWS serves only the key. These two paths never merge at the edge. Even if someone intercepts CDN traffic, the content is useless without the license. This is why engineers lose sleep when license servers have latency spikes. Video bytes flow through Open Connect. Everything else runs on AWS. Netflix's control plane is 700 plus microservices deployed across 3 AWS regions, US East 1, US West 2, and EU West 1, active. The 2012 Christmas Eve outage made multi-region non-negotiable. The account service handles authentication and subscription state. The playback manifest service generates per-user CDN URL lists. The streaming health service monitors quality of experience metrics in real time. Netflix open-sourced much of this infrastructure. Eureka for service discovery, Hystrix for circuit breaking, Zool as the API gateway. These tools are now part of Spring Cloud and power thousands of production systems outside Netflix. But none of this matters if individual services can't survive failure, which is exactly what chaos engineering tests. Netflix deliberately kills their own production systems every business day. Chaos Monkey, their open-source tool, randomly terminates live EC2 instances during work hours. The rule is simple. If your microservice cannot survive random instance death, it gets fixed before a real outage causes it. They extended this with Chaos Kong, which simulates the failure of an entire AWS region. This validates that traffic reroutes correctly and users feel minimal disruption. The result, Netflix achieves 99.99% playback availability under 53 minutes of downtime per year. YouTube ran a similar postmortem after their 2018 outage, 1.5 hours of global downtime, and hardened their multi-region failover identically. The lesson: you cannot trust resilience you have never tested under fire. Here's the circuit breaker pattern Netflix open-sourced as Hystrix. The circuit has 3 states: closed, open, and half open. When failure rate crosses 50% within a 10-second window, the circuit opens. All calls fail fast immediately, no waiting for timeouts. After a 30-second cooldown, the circuit enters half-open state. It allows one probe request through. If the probe succeeds, the circuit closes and traffic resumes. If it fails, the circuit opens again. This pattern prevents cascading failures across 700-plus microservices. Without it, one slow downstream service creates a thread pool storm that takes down the entire control plane. Netflix's 2012 outage propagated exactly this way. One misconfigured deployment starved thread pools across dependent services. Netflix's architecture is not magic. It is layered engineering decisions built on top of one another. ABR streaming solves the bandwidth mismatch problem across 190 countries. Per-title encoding saves 20% bandwidth globally without quality loss. Open Connect puts 17,000 servers inside ISP networks, dropping RTT from 80 milliseconds to 3 milliseconds. The AWS control plane runs 700-plus microservices across 3 active regions. Chaos engineering ensures 99.99% availability by breaking things before users do. Every one of these patterns, CDN edge caching, adaptive quality, circuit breakers, multi-region active, applies to any high-throughput content delivery system you build. Netflix is the blueprint. The numbers are the proof. Netflix does not stream video. They stream trust. Every architectural choice exists to make buffering impossible. The real insight, the best CDN, is the one inside your user's ISP. If you found this useful, subscribe. Next video breaks down how YouTube built Quick Protocol to kill TCP rebuffering on mobile at 1 billion hours per day.